Now let's discuss another type of thermodynamic cycle, and which is refrigerators or and heat pumps. Now the basic idea is that, now let's talk about heat engine again. So as we already discussed in very detail, the objective of a heat engine is to produce a work, right? And in order to produce a work, we need to put heat to a system. Now, then the coming along, the question is that now, can we really reverse a heat engine to use the thermodynamic cycle for something else? Now, in other words, can you really take heat from a low temperature reservoir or a high temperature reservoir by supplying work to the cycle? Okay. Now, in that case, our objective is not on the power output, but it's more about, can we really make use of this heat, to make a certain place cool or make a certain place warm. Okay. So we can draw the schematics for refrigerator or heat pump cycle as this. Okay. Still, we need a warm environment, but it's not heat source. Just remember that. And we also need another kind of cold refrigerator spaces. Again, that is not heat sink. Actually, that is kind of the opposite. But in the middle, we have a cycle. And now, instead, the objective of this cycle is not to produce the work. Instead, what if we just try to input a work, as you see here, W net in. Okay. Then by putting a certain amount of work to the cycle, can you really take a heat out of this cold space in terms of QL? Okay. And dump this heat, certain amount of heat, to a warm environment. Okay. So now if you really think about how we use a refrigerator, in that case, the objective, the purpose of having a refrigerator is to make inside the refrigerator very cool. So in that case, now QL should be your desired output. Okay. Now, and also if QH should be if the QH is your desired output to make a certain place warm, like kind of your room or your house, and we call that as heat pump. The thermodynamic point of view is the same thing, but objective is different. It's a cold place is your objective, or warm space is your objective. So that is that depending on this objective, we sometimes use it as a refrigerator, or we use the same cycle as a heat pump. But now, same thing, same way as we did before. If we take cycle as your system, okay, which is a thermodynamic cycle, and now the internal energy change inside of your system should be 0 because that is a cycle. And that is written as QL minus QH. And now we have minus, but we have work input, so we should write it this way. Okay. So what you can write it is the amount of work, net work, that we have to input to the system is balanced with QH minus QL. Okay. So if this cycle is used for refrigeration, then now QL should be your desired output. So for refrigerator, your desired output QL can be written as QH minus W net in, or heat pump, where you want to use QH to make your space warm, that can be written as W net in plus QL. Okay. Now let's try to make one example. Okay, so This is the vapor compressor refrigeration cycle. That is basic cycle that runs your refrigerator at home. Okay? Now, if you really open up your refrigerator, you have these four main components. Okay? One is a compressor, and second one is condenser, and expansion valve, and evaporator. Okay? And that is whole your cycle. And now, same thing as we discussed, we need a warm environment to dump heat out, and also we should have a cold, cold reservoir that we take heat, from this cold reservoir to the evaporator. And now, the objective of this refrigerator again is here how we can make this space cool. So that is your inside a refrigerator. Okay, now how we can make that refrigerator cool by taking certain heat, in the case QL out. Okay? So that is our objective. And now in order to take this heat, first of all, we should, so the working fluid of this refrigerator is, refrigerant, and we call that as R. Generally we use R134A. But what it does is now we compress the vapor of refrigerant by putting that much of power to run the compressor. Then this refrigerant that becomes hot, that goes to the condenser, and the refrigerant vapor is condensed. Okay? And the heat, that is basically rejected during the condensation should be transferred out to, in the case, warm environment. So that in the case, this one is your, let's say the kitchen. Okay, my kitchen room or kitchen. Okay, where your refrigerator is located. And then this kind of condensed refrigerant goes to the expansion valve to make an expansion, but in the case we don't have any work out, so no work, because there's a simple expansion, so there is no working component inside the expansion valve, so there should be no work. But as a result of expansion, then we have a low pressure and we have kind of very cold refrigerant. Then this cold refrigerant goes to the evaporator. Then, this refrigerant evaporates, and in order to evaporate, that it needs to heat input, and this heat input is taken out of the refrigerator space. Then after evaporation, the refrigerant goes back to the compressor. We are going to discuss a lot about details of how we run this refrigeration cycle, but that is what it is. Okay. Now, by running this refrigeration cycle, then we can make this inside refrigerator very cool. And as a result, in return, we have to dump heat out to your kitchen. So usually when you go home and the kitchen, you can feel warm, if you just stand nearby the refrigerator. So that is why basically this whole heat out of this refrigerator is the kind of main source that you feel warm by standing outside, standing nearby the refrigerator in the kitchen. Okay. Now, then how can we understand the efficiency? So we have to use the same, the definition of general efficiency, which compares desired output with required input. But now, instead of using efficiency for refrigeration cycle, we use a new term that is called coefficient of performance, or in short, COP. But COP is basically conceptually same as efficiency. Okay. Now the COP is defined for refrigeration. Then we just put subscript R here. Okay. Then COP subscript R is defined as the desired output, to the required input. And now for refrigeration cycle, the refrigerator, the desired output is how much heat can be taken out of the cooled surface, cooled space. And now the required input should be the amount of work that should be input to the cycle. Then from the first law of thermodynamics, where we wrote down here and here, so W net in can be written as QH minus QL. So the final equation for refrigeration can be expressed in terms of QL divided by QH minus QL. And now, how about heat pump? Again, the cycle-wise is exactly same as a refrigeration cycle, but now instead of focusing on how we use QL, now we focus on how we use QH. So now your purpose is to, it's about how we can make a space warm. Okay? Then that is a nice example, the representation. So now we have refrigeration cycle. Okay, then that still needs certain amount of work to run this cycle, and we need a heat input from a cold outdoors. So in that case, that should be your outside house. Okay, so let's assume that there is winter. So now outside your house is at very kind of cold, the temperature, like in the case, let's say that 4 degrees Celsius. Even from this cold outdoors, we take certain heat to the system. Okay. Then, as a result of running this cycle, then the amount of heat that should be transferred out from this cycle is the summation of W net in and QL, because we have two arrows into your cycle. Then your QH should be 7 kilojoule. And this much of 7 kilojoule is used to warm your house. Okay, does it make sense to you? So again, the cycle-wise is still the same, but whether we want to make use of QL to make your space cool, or make use of QH to make your space warm, we call that the former as a refrigerator and the latter as a heat pump. And now, similarly, we can define the COP for heat pump. In the case, in order to distinguish the COP for heat pump from the COP for refrigerator, we put subscript HP. And this COP for heat pump has desired output, not QL but QH. Compared to the required input, still the same, W net in. Okay. So the final equation for COP for heat pump can be written as QH divided by QH minus QL. Okay. Now, from the first law of thermodynamics of your refrigeration cycle, okay, again, we always have QW net in is Q, what is that? QH minus QL. Okay. that should be always positive. So from this relation, okay, or QH is always can be written as W net in plus QL. So we can conclude that whether you talk about refrigeration or whether you talk about heat pump, right, QH should be always greater than QL. Okay? So what it means is that by comparing COP for HP and the COP for refrigeration, always COP for heat pump is greater than COP for refrigerator. Okay. And this relation can be written as COP HP should be COP R plus 1. Okay. So that is what I have here.